G'day, I'm James, and welcome to the beauty and the thinking behind vectors and matrices. This is the third lecture on the series about matrices, and we'll finish up that topic today. But let me start with a puzzle. Let me start with a theorem, first of all, about geometry. You may have seen this result about triangles. So here's a random triangle, just cut it out randomly. I'm sure it's scalene. I'm sure all three sides are different lengths. And what I want to do is work out the midpoint of each side. For example, I can work out the midpoint of this side by bringing one corner up to the other corner and just make a little pinch right there. There's the midpoint. I can work out the midpoint of this side by doing the same thing. Bring a corner to a corner, fold that edge in half, which means I've got equal lengths there, must be the midpoint, and I'll do the third midpoint. The third midpoint indeed. There it is. Great, so I've just worked out the three midpoints of that triangle. You probably can't quite see them. But what I'll do now is actually draw the lines from each corner of the triangle to the midpoint on the opposite side. So there's one line there, one line will be there, and one line will be there. In fact, they're called the medians of the triangle. All right, so I actually got a marker. Where is my marker? Here it is. Let me do it so you can actually see it on the camera. So I'll do my best because I'm only going to freehand draw this, but midpoint to corner. It'd be a line that's like that. I think I did a pretty good job there. Now let me go corner to this midpoint. And it's a line that's like, whoops, a little bit, doing my best. It's meant to be straight. Whoops, I failed up there. Okay. And the third one, corner to midpoint. Now here's the magical thing. When you do this with the three lines, and if you did it actually very carefully, if you actually measured it with rule and everything, oh yeah, it worked out, you will find all three medians are sure to go through a common point. No matter what shaped triangle you draw, those three lines from corners to midpoints are sure to be concurrent, go through a common point. And more is true. Obviously, this is half the bottom length, half, half. This is half the bottom length, half, half. This is half the bottom length, half, half. But the amazing thing about this position here, that this point is 1/3 of the way along that median. It's 1/3 of the way along that median, and 1/3 of the way along that median. That common point divides each median into thirds. So we've got halves on the sides and thirds along the medians. Kind of crazy. All right, so that's a theorem in geometry. One can actually prove that. You might have proved that already, or prove it someday in a geometry course. But here's my actual puzzle for you. This is without any coordinates. What if I actually gave you a triangle like this one? I told you this coordinate's lying at the position 2, 5 on the coordinate plane. This point's lying at the position 10, 9. This point's lying at the position 3, 13. If I actually did do this and had the three medians, which I know are going to go through a common point from geometry, here's my challenge for you. Can you now work out the coordinates of that special point there? I actually want the coordinates of this point of concurrency. And remember, I told you it's halfway along here, and it's 1/3 of the way along there. Halfway along there, 1/3 of the way along there. Maybe those facts are enough for you to figure out the actual coordinates of one of these points. All right, so we'll solve that at the end of today. Actually, the story of vectors will help us do this. So that's our motivation. So keep this in the back of your mind, and let's get cracking with the lecture on vectors. Good stuff. Okay, the first issue at hand. What is a vector? All right, well, I'm going to say a vector is simply a shift. That's a very loose definition. What do I mean by that? But it's actually a very good intuitive definition. What do I mean by shift? So imagine you've got some town. Here's a town, a map of the town, and it's hit by an earthquake where all the points in the town just move. The earth just moved under this earthquake. And every point moved, say, 2 units right and 1 unit up. Every point shifted. That shift is a vector. Here's a picture of a vector. This point shifted 2 right, 1 up. This point shifted 2 right, 1 up. 2 right, 1 up. Every point shifted 2 right and 1 up. Even this point I didn't draw shifts 2 right and 1 up. This point 2 right, 1 up. A vector is a shift. It's a picture of all the possible arrows one can draw for points moving 2 right, 1 up. Now here's the trouble. We are human. We cannot draw arrows for every single one of those points. So we tend to just draw a few examples of arrows. But the picture of an arrow, if you just draw one arrow, means a shift where all points move. Every single point moves. Keep that in your mind. Every single point moves, even though you might be just focusing on one point, drawing one arrow. For example, people do this. If I make this more mathematical and give you an actual point, I'll call it A. Here's A, has coordinates 1, 2, 3, 1, 2, 3, 4, so it's the point 3, 4. I can ask, where does that shift? Well, it would shift 2 over 1 up. up in this vector to this point here. I'll call it B, which is 2 over, makes it 5, 1 up makes it 5. Bingo. There's the vector that shifts the point A to the point B. In fact, people might even write this as the vector that shifts the point A to the point B. This is one actual arrow, but this arrow is meant to represent this entire picture of all possible arrows. One arrow representing all possible arrows. Okay, so whenever you look at books, they'll probably only ever draw you one arrow, but it means all possible shifts. For example, I'll give you another one, like this point here, I'll call it R. 1, 2, 3, 4, 5, 6. It has coordinates 6, 0. Under this vector, where does it shift? It will go 2 over, 1 up. Go to this point S, which is what now? 8, 1. 2 over, 1 up, yeah. Bingo. So there's the vector R to S. The vector shifts R to S. In fact, this vector shifts R to S. Here's the notation. But here's the funny thing. That is one arrow. That is one arrow. But each arrow represents this entire shift. These are the same vector. They're the same vector. I just have to draw two different arrows that are shifting for the same transition here. All right, got that? A vector is just a shift of all the points in the plane. Voila. So let's go for some notation now. There's some tricky notation here. V for vector. I might want to use the letter V to denote a vector. So I might call this the vector V. People tend to use small letters for vectors. I don't know why, it just happens. And here's the awkward thing. In textbooks and in printed matter, they use a bold V, like they print in bold text, which is very hard for us to draw when we just do it with pencil and paper. So on pencil and paper, what people tend to do, and you probably don't see it because people don't do it that often, but do a V with an underscore and underline it. That just means it's meant to be bolded. Okay, so people tend to use bold letters for vectors, and if you can't draw a bold letter, put an underline instead underneath to say, I mean it to be bold. Okay. Now, 2 over and 1 up. We can actually represent that. Here's the tricky thing. Here's a disconnect between what I do as a mathematician and what your textbooks probably do. As a mathematician, I would represent this as 2, 1. I won't use round brackets because that looks like a point, so mathematicians tend to use angled brackets. V is the vector 2, 1. Shift 2 to the right and 1 up. Schoolbooks don't tend to do that. In fact, they follow the convention of what we were doing in the previous lecture, the last lecture, about matrices. Do you remember last time we were writing points not as matrices that are 1 row and 2 columns? We found it necessary to switch it around and write points as 2 rows and 1 column. So people tend to do the same thing here in the school world. They don't do what I did, write 1 row, 2 columns, and I use angled brackets. They tend to go back to the same notation and use 2 rows and 1 column. So in your books, you might see this vector is 2 to the right, 1 up, written as a column. That's a little irritating. I admit that's very irritating, but there it is. So this vector here, V, is denoted 2, 1, but written as a column. All right, there's more notation, more notation. You might have heard this term position vector of a point. So if I give you a point, I don't know, it's like this point P, position vector of P. What do I mean by that? Well, I've got one point in the plane, but there's also actually a very common second obvious natural point to work with in the plane, namely the origin. The origin feels special, usually denoted with O and has coordinates 0, 0. So when people talk about the position vector of a point, they say, oh, what would be the vector that shifts the origin to the point P? That is, that vector. What is that vector that shifts the origin to the point P? Well, I've been chosen a very special point here because the vector that goes 2 to the right, 1 up, takes the origin to P. So I've got the position vector OP is 2, 1. I made sure it's this one. The position vector of this point is the shift you need to go from the origin to that. It's this vector again. So now I've got this vector, this vector, this vector, and this vector, and they're all the same. This vector V is the vector AB, is the vector RS, is the position vector of the point P, what shifts O to P, and it is this particular formula. There are all the notations of vectors. Small bold letters, maybe actual examples of points that got shifted, maybe just where the shift of a particular point P is from the origin, or you might be given the actual formula for the vector. But each and every single time, a vector means all possible arrows you can draw that shift all points in the plane. Got that? Okay, so that's what we're going to work with from now on. So let's keep playing with shifts. I kind of like this earthquake example. It's a little sad because I don't want people to get hurt in an earthquake, but it actually shifts everything in town. You can actually start thinking that way and actually get some good results mathematically. So let's now start playing with vectors. Okay, what do we think we mean by the magnitude of a vector? If I ask for the magnitude of an earthquake, one of high magnitude is very strong, does a lot of damage. One of low magnitude is not so weak, is actually okay. Actually, so a very strong earthquake, think about it, would actually shift things a lot. And a very weak earthquake would just shift things a little bit. So the distance things shift is a measure of the strength. So people say that about vectors. The distance this vector shifts points is a measure of its strength. They call that the magnitude of the vector, the length, the distance things move. Could I work out the length of a vector? Well, yes. If I give you the actual numbers that correspond to this vector, namely this one goes 2 units to the right, 1 unit up, we can now measure the length of that vector, the magnitude. That is, we've got a right triangle. I can't help but think of Pythagorean theorem right now. People denote the length of a vector, the magnitude of a vector, with just bars. So the length of v is given by Pythagoras. The square root of 2 squared plus square root of 1 squared plus 1 squared is the square root of 5. This length here is root 5. This vector shifts all points root 5 units along. Its magnitude is the square root of 5. Yes? All right. Mathematicians actually use double bar notation for the magnitude. So you might see that in some of the reading you do. I think most school books just use single bars. So just watch out, there could be some change of notation on you. No big deal. All right, so let's do another example. Suppose I give you a point here, I know, well, let's do it in blue so it looks different. Say 2, 7, and a point down here, say -3, 5. And let's consider the vector that shifts this point down to this point. I'll call it W, a bold W, but I can't do bold, I'll do underscore instead on paper. All right, so there's a vector, in fact it shifts all points like that, but I've given you 2 specific points to actually, 2 specific points to work with. All right, what is the magnitude of that vector? Well, I could use Pythagoras to work out the length of that vector. I can see it's gone what? We've gone from 7 high to 5 high, so that's 2 high there. We've gone from 2 to -3, that's the distance of 5 there, so -5 units that way. The length of this vector is square root of 5 squared plus 2 squared. The length of this vector must be the square root of 29. That's it. Magnitude of a vector is just the distance a vector shifts points. And you can use Pythagoras to work out what that length is. Cool. Okay, here's our poor town. It went through an earthquake that shifted everything 2 right, 1 up. This vector v. Now suppose this poor town was hit with the same earthquake, but now double the strength. So instead of a point just going from there to there, it now goes twice as far from there to there. In fact, I'll try to draw it. This point now shifts twice as far to over there. And this point here shifts twice as far to over there. Every point shifts twice as far. In fact, now we can see what that new vector is. It used to go 2 over and 1 up. Now it'll go twice as far, 4 over and 2 up. So a double the strength vector, seems very natural to call that twice v, would just be double this and double that, 4, 2. In fact, if it was hit with an even stronger earthquake that tripled the distance moved, went say once, twice, thrice over here, that's 3v, 3 copies of v. It'd be, this distance used to be 2, now it's 6. This distance used to be 1, now it's triple that, 3. 3v would be 6, 3. In fact, suppose it was hit with a very strong earthquake, 100 times as strong, that it'll move 100 times as far to the right and 100 times as far up. We're doing what's now called the scalar multiplication of vectors. All right, so we can actually scale the strength of vectors up by multiplying the components by a particular number. Double the strength vector gives an arrow twice as long in that direction, the components double. Grand. In fact, suppose we had an earthquake that did the exact opposite of v, went in the reverse direction. It would be an earthquake that does this. Instead of moving this point, say, this way, 2 units and 1, it now moves the reverse direction, exact opposite. It now goes 1 down and 2 to the left. Okay, there's the reverse vector. It's shifting every point in the reverse direction. So it seems natural to call that negative v, in which case it goes -2 units horizontally and -1 units downwards. In fact, if we had an earthquake twice the strength and in the opposite direction, points like this would move, instead of moving 2 units that way, it will now move 2 units this way. One vector, another vector. Now you can see there will be -2 down, -4 to the left. So -2v would be -4, -2. -4 in the horizontal, -2 in the vertical. In fact, a really strong earthquake in the opposite direction would be something like -100v, which would be -200, -100. This is scalar multiplication, and you can see what it's doing pictorially, and you can see what it's doing to the actual numbers if you've got the numbers at hand. Great. All right, let's carry on. Okay, a practice problem for you. A is the point -1, 6, B is the point 2, 4. First question, what is the magnitude of the shift from A to B? Next question, what is the magnitude of 7 times the shift from A to B? In fact, I'm wondering if the answer you get there is this answer, the magnitude of 7 times the shift of A to B, 7 times the value of just the ordinary shift from A to B? Does a factor of 7 just come out? Try it out. What does the mathematics show you? Okay, here's a question we can do together. Point P has coordinates 1, 1. Point Q has coordinates 10, 7. And here's the line segment connecting P to Q. The question is, find the coordinates of a point R that is 1/3 of the way along this segment. I want this to be 1/3 of the whole segment. Can we do that? All right, so here's how my brain works on this one. So think about shifts. How would I shift to go from point P to point Q? Well, first of all, I need to go some distance horizontally, and then I have to go some distance vertically. In fact, I can see to go from 1 to 10, I need to go 9 horizontally, and to go from a height of 1 to a height of 7, I need to go 6 vertically. Now, that's the shift from P to Q, but I only want 1/3 of that shift, because going 1/3 of that shift will get me to the point R. Oh, which means I need to go 1/3 of the way along horizontally, so that'd be 3, 1/3 of 9, and I need to go 1/3 vertically, which would be 2, 1/3 of 6. So the point R must be going from P, 3 over and 2 up. So if P is coordinates 1 and 2, R must have coordinates 3 over horizontally, 1 plus 3 is 4, 2 up, 1 plus 2 is 3. Here's my answer. R must be the point 4, 3. Did you see that? That's going to be 1/3 of the vector from P to Q is the vector P to R, and R has those coordinates. Grand. All right, here's a practice question for you. 3 points, K, Q, and L. Q is somewhere on the line segment connecting K and L. In fact, KQ to QL comes in a ratio of 2 to 3. KQ, that length, QL, that length, this length to that length is a ratio of 2 to 3. So it's 2 things versus 3 things. All right, given that, which of the following 3 statements are true? Maybe all are true, maybe none are true, maybe some are true. Which of these 3 are true? Namely, shifting from K to Q is 2/5 of the shift from K to L. That's the first statement. Is that true? Second statement, 1/3 of the shift from Q to L equals 1/2 of the shift from K to Q. Is that true? And the third one is, shifting from Q to L is the same as doing -1.5 of a shift from Q to K. Is that true? See if you can think your way through these. Which of these 3 are actually true? Give it a try. Okay, let's now start combining vectors. Imagine our poor town was first hit with the earthquake V, shifting everything 2 right and 1 up, and it's hit with another earthquake, this vector W, shifting everything 2 right and 6 down this time. What's the combined effect of the 2 earthquakes together? That is, what is doing earthquake V followed by earthquake W do to points? All right, so let's find out. Let's actually draw it. I've drawn some graph paper here, so I'll do it geometrically and try to be neat and correct. Let's choose a point like this one and see where it shifts when you first do V and then you next do W. So first doing V shifts things 2 right and 1 up, so it shifts the point to there. Then that point gets hit with W, which shifts everything 2 right and 6 down. 2 right and 2, 4, 6 down gets me there. There's W. All right, so a shift of W, and there was a shift of V. So this poor point started here and went end up down there. So the combined effect is this shift from there to there. And remember, that's not just true for that one point, it's actually true for every point in the plane. Vectors represent every point in the plane. But that's it, we've got the answer. So if things shifted, what, 4 places to the right, 1, 2, 3, 4, and 1, 2, 5 places down. So the net effect shift is 4 over 5 down. In fact, the good notation of this would be, we did shift V, and then we added shift W, and we got the shift 4, negative 5. Now actually, think about this. The arithmetic here is kind of natural, because first we shifted 2 to the right, followed by 2 to the right, and we got 2 plus 2, 4 to the right. And then we shifted 1 up, and we also shifted negative 6 up, and 1 plus negative 6 corresponds to negative 5 up. So actually, to add vectors, all you have to do is add the horizontal shifts, the actual numbers, 2 plus 2 is 4, add the vertical shifts, 1 and negative 6 is negative 5, and that actually does match the actual vector you get from the combined effect of V and W. Oh, so in which case, if I did it in the reverse order, W and then V, it'll be the same numbers. 2 plus 2 is 4, negative 6 plus 1 is negative 5. It should give you the same answer, 4, negative 5. So it looks like V plus W equals the same thing as W plus V. It doesn't matter in which order you add vectors. In fact, that's very clear from the arithmetic. Actually, you can kind of see it from the geometry too. This was V plus W, got this shift in black. Well, if I did W first, start this point, hit it with W, which is 2 over and 2, 4, 6 down, gets me to there. Do W first, and then hit it with V, W plus V, 2 over 1 up, and look, we're at the same place. W plus V gives me the same total shift as V plus W. In fact, you can kind of see why that's true geometrically, because I've drawn here a parallelogram. V plus W is 2 sides of the parallelogram, W plus V is the other 2 sides, and they both give the same diagonal. So this must be true. Adding vectors either in geometry or in arithmetic show you that it doesn't matter what order you add them, they commute. Grand, grand. All right, so we can now add vectors. In fact, we can also subtract vectors. Let me give myself some space. Let's look at this question. Let's sketch the vector V minus W. That is, I want to first apply the shift V, and then I want to add to that the shift that's the opposite of W. Negative W is the opposite of W. So let me do it geometrically on the board first. So let's choose a point. Let's see if I can get it nice. I'll choose that point at random. First apply V, 2 over and 1 up. That's going to be in red. 2 over 1 up, there's V. And now I want to add to it the opposite of W. That is, W goes this way, I want to go that way now. So instead of going 2 to the right and 6 down, it'll now be 2 to the left, and 6 up. 2, 4, 6, there. So this is actually not W, it's the opposite of W. And the next shift is from there to there. There is the sketch in black of the vector V minus W. In fact, it has coordinates, no shift horizontally, 0, and 2, 4, 6, 7 up. So this actually is the vector 0, 7. Beautiful. And in arithmetic, you can see that as well, because look at this. A horizontal shift of 2, take away a horizontal shift of 2, gives me a horizontal shift of 0. A vertical shift of 1, take away a vertical shift of negative 6. Sorry, my board gets smudgy. 1, take away negative 6 is positive 7. So you can see it in arithmetic as well. All right. So now we know how to add vectors, subtract vectors. We can multiply vectors by numbers. I can do 2 W's, I can do 17 W's, I can do 74 V's. We can now play with vectors to our heart's content. So Let's play. Okay, here's a very complicated, scary looking practice problem for you. It's this. Here's a diagram. A, B, C, D, making this quadrilateral. First of all, just to warm up, do you see that the shift from A to C equals the shift from A to B plus the shift from B to C? Look at that. If I shift from A to B means I'm shifting, and I add to that a shift from B to C, the net effect is I've gone from to there. It is the shift from A to C. Shifting from A to C is the same as shifting up to A to B and then shifting B to C. That's the game we're kind of playing now. All right, so here are the questions for you. Part A, which of the following statements are true? The shift from A to D is the opposite of the shift from D to A. The shift from A to B plus the shift from B to C plus the shift from C to D is the same as the shift from A to D. Is that true? And then this complicated one. The shift from A to D plus the opposite of shifting from A to B plus the opposite of shifting from D to C turns out to be just a shift from B to C. My brain hurts. All right, and then I've got part B. What is the total effect of the shift those three things combined together? What's the total effect of doing those three shifts together? And final question is, mark anywhere on the diagram a point P for which the shift from A to P is the same as the shift from P to D, that these vectors are the same. I was using the word shift because I think it's good to think in terms of shifts, but these are all about vectors, obviously. All right, good luck, give it a try. Okay, let's do this one together. Here's a diagram, a vector A, a vector B, and a vector A again, so I guess they are exactly the same shifts. This was a good diagram. And some dotted blue vector W. And the question is, what is the vector W in terms of the vectors A and B? All right, so W wants to shift from here to here. So what I want to do is I could do, first of all, shift along A, then shift along the opposite of B, and then shift along A again. Those three shifts together correspond to shifting from here to here, which is what W wants. So W must be then, all right, first shift along A, great. Then shift along the opposite of B, plus negative B, oops. Then shift along A again, plus A. So W must be A minus B plus A. And since we know that everything's like algebra, things commute and all the rest with vectors, I can rewrite this as 2A's, take away B. W is 2A's, take away B. Beautiful, beautiful. That's the game we're playing. Here's another practice question. Consider the vectors R and S shown on this diagram. So I've just drawn one vector, one arrow for R, but it represents all possible shifts like that. I've drawn one arrow for S, but it represents all possible shifts for that. So here's my question for you. On your own graph paper, sketch arrows that represent the following vectors. Please sketch a vector 2R, negative S, 10R, 1/2 of R plus S, R plus 2S, 2R, take away 3 S's, and S minus R. All right, so there's a lot of sketching for you. Give it a try if you like. Could be kind of fun. I guess you need a lot of graph paper. Good luck. Okay, here's a practice problem we'll do together. Here's a triangle ABC, and M is the midpoint of the side BC. So this length equals that length. And I'm going to do some labeling here. In fact, I'll call the vector that shifts from A to B the vector B. So that's the vector B that shifts from A to B. And we'll call the vector that shifts from A to C, we'll call it C. The vector that goes from A to C, that shift, we'll call C. And the question is, find the following vectors, these 4 vectors here, in terms of B and C. That is, how can I describe the shift from B to C? All right, we'll do that first. I want to shift from B to C. Well, one way I could do this, first shift the opposite of B, and then shift C. So I could say that actually this is equal to the opposite of B plus C. Opposite of B plus C is the same shift from there to there. And if you like, I could rewrite that as C take away B. That's the game we're playing right now. Do you see how it's going to work? In fact, if I want to shift, say, from just B to M, how do I think of the shift from B to M? Oh, if M's the midpoint, I just want to do half the shift from B to C. Half the shift from B to C is the shift from B to M. So if that's the shift from B to C, the shift from B to M must be half of this. Half of C, take away half of B. Sneaky, sneaky. The shift from M to C. Shifting from M to C is the same as shifting from B to M. They're going to be the same shifts, in which case the answer is the same. Haha, that's actually sneaky that time. To shift from A to M now, I'm going to start at A and somehow get myself shifted over to M. How would I do that? Well, I could go B and then do the shift from B to M, which I've worked out. So it could be just do B and then shift from B to M, which is this formula. So it's B plus half of C minus half of B. So that equals a B, take away half of B, that's half of B plus half of C. My handwriting's going to get a bit scrawly, but hopefully you're following just fine. Do you get the feel for this now? Is this starting to make some sense? How thinking of vectors as shifts can actually help you out? Good stuff. All right, here's yet another practice problem for you. 4 equilateral triangles are arranged as shown. 1, 2, 3, 4. Big equilateral triangle. Let OA be the vector A, let OB be the vector B. Please write the following in terms of A and B. There's the shift from O to C, the shift from A to B, the shift from C to D, the shift from O to D, and the shift from A to E. Can you rewrite all those shifts in terms of the basic ones, A and B? I bet you can. And then, if the magnitude of A is 7.5, what's the magnitude of B going to be? What's the magnitude of A minus B going to be? And a final, out of the realm question, what transformation of the plane maps this triangle into that triangle? What geometric transformation, like we were talking about last time, does that sort of motion? Turns this small triangle into this big triangle. All right, give it a try. Okay, let's talk about why we care about vectors. Why are they useful? What do people use them for? Perhaps I should have talked about this early on. Okay, people love it to understand the physical world. So physicists use vectors all the time. For example, here's a very simple physical system. It's just a pendant hanging on some string. But think about this. This pendant is not moving, but it's experiencing forces that want it to move. For example, gravity is trying to shift this pendant downwards. There's some sort of shift due to gravity, it wants to go downwards. But this string is taut. This string is taut, so it's pulling it this way as well. So there's a vector trying to shift the pendant back that way along the string. And there's another vector trying to shift it this way. This string on this side is also taut. That tension's trying to pull that pendant that way. But the pendant's not moving. So it must be the combined effect of these three shifts, this shift down, this shift over, and or maybe it's more like this shift up, must correspond to no shift at all. In fact, if we can see it's no shift at all, it's not moving. There is no shifting going on. So physicists like to look at force diagrams. They'll draw the various forces in some system and figure out which forces are acting where and which force wins in the end to make things shift, make things move, or keep things static. So this is like classical mechanics used in physics, uses vectors all the time. That's the sort of thing we're doing. We're adding vectors here. I add them all up. Those three shifts correspond to the zero vector, no shift at all. All the work we've been doing with adding and scalar multiplication of vectors is pertinent right now to study physics. Okay, let's now go back to the very beginning puzzle about the medians of a triangle. They all happen to go through a common point. A median goes from one corner to the midpoint of the opposite side, and it turns out this common point from geometry is always 1/3 of the way along the medians. And my challenge was you to figure out, is there a way to not actually prove this point exists, that's what geometry does, but to actually find the coordinates of that point if I give you the coordinates of the corners of the triangle? And I bet we can now. So let's do it. So first I'll just focus on one median, which is halfway across to the midpoint, and then 1/3 of the way along to that special point. That's going to do it for us. Our vector thinking will help. First of all, can we get to this midpoint? What are the coordinates of that midpoint? Well, to go from this corner to that corner, I have to shift, looks like 8, and then I have to shift 4. So this is a vector shifting of 8 across, 4 up. But the midpoint only wants half of that. So I'll do 4 across and 2 up. 4 across and 2 up will get me to that midpoint, which means the midpoint is going to be 2 plus 4 is 6, 5 plus 2 is 7. There's the coordinates of the midpoint. Next, to find that special point P, I need to go 1/3 of the way along from M to this top point. Now, to go from M all the way to this top point, that's a 6 to 3. It's a shift of -3. 7 to 13 is a shift of 6. So the shift from there to there is that vector. But I only want 1/3 of it. I want 1/3 of it, which would be a shift of -1 and 2. All right, so I'm going to go from 6 and do a shift of -1 and 2, must get me to the point 5, 6 plus -1, and 9, 7 plus 2. Bingo. There are the coordinates of that special point where the medians of a triangle intersect. We could do that for any set of numbers one's given and come up with a point there. But notice something beautiful. There's actually something lovely about this formula. Look at the x-coordinates. 2, 3, 10. 2 plus 3 plus 10 is 15. Divide that by 3. You get 5. The average of the 3 x-coordinates is 5. Look at the y-coordinates. 5, 13, 9. 5 plus 13 is 18, plus 9 is 27. Divide that by 3. 3 numbers divided by 3 gives me the 9. The average of the 3 y-coordinates is 9. This is true in general. Are you able to prove that special point in a triangle where the 3 medians intersect is given by the coordinates the average of the 3 x-coordinates and the average of the 3 y-coordinates? That is so beautiful. That just hangs together gorgeously. So can you prove it's actually true? It is. What's the theory behind that? Give it a try.